Oh, she's there.
Oh, just join. Yeah.
You're worried.
Worried of what?
You were like, we thought you were not coming. Because people, like most of the people, just left.
Oh,
Mm-hmm.
I'm here now.
Right, miss.
Okay. So we will do impulses, momentum, and impulse, and that is almost it's our last topic that we're gonna cover. So momentum and impulse. So what is momentum and what is impulses when we talk about that? Okay, so to define momentum, let's first assume there's a car speeding towards you, so it's coming towards you with a very higher speed. Okay, or maybe the brakes are not working. So can you stop it just by standing in front of that car? So obviously you would not. Okay, why? Because the car is big in terms of its mass, and number two, the car is in motion. Okay, so to define momentum, so momentum is the measure how difficult it is how difficult momentum is defined as, okay, it's the measure of how difficult to stop an object in motion. Okay, so when an object is in motion, because of its speed and because of its mass, so it's very difficult to stop an object which is in motion. So it means the momentum depends on the mass and on the velocity. So momentum is a product of the mass, okay, of an object. So it's a product of a mass and it is velocity. Okay, so it means it's the mass of an object in motion with its speed. So we denote the momentum with P, and the momentum is a vector. Okay, so it tells us in which direction. And the direction of the momentum is the same direction as that of the velocity. Okay, so in the SI units, it's kilogram times meter per second. Okay, so just from the calculation, with the momentum being equals to mass, which is should be in kilogram, and the velocity which is being in meter per second. Okay, so you will find other units like Newton per second, but it is SI unit is kilogram meter per second. Okay, so the object momentum will change. Why? Because the velocity changes. Okay, so it depends. So the momentum will change depending. Okay, the direction of the momentum will change depends on the velocity of the, the direction of the velocity. Okay, and the momentum changes depends on depends on the mass and on the velocity. So the higher or the more mass the object has, or the more velocity the object has, then the more momentum that object will occupy. Okay, so in order, as we said, in order for the object to move, in order for the object to be in motion, then there is a force required. Okay, so it's the same thing here. In order for the object to change momentum, then there is a force required to be applied to that object. Okay, and the rate of change, remember, okay, so the rate of change in momentum of an object is equal to the net force applied to it. Okay, so this one, it means that depending on the amount of force applied to an object, then the momentum will also changes depending on that amount that is being applied to the object. Okay, so if you have forces that are applies to an object, okay, then depending on the net force of that of those forces, when you sum up all those forces together, then that will determine the change in momentum of that object. If there is no forces, no external force, you know, if the external force is equal to 0, okay, then we are saying that the momentum of that object is equal to 0. Because if there is no net force, then if you calculate the change, then it's equal to 0. Because the velocity at every point is constant. And we said that, if you remember, from the Newton second law, it's saying that, from the Newton third law, it's first law, it's saying that, so we have, if the force is constant, then the object is not accelerating. So in order for the object to accelerate, then there should be a net force applied to that object. Okay, so if we consider, if we consider a mass or an object of mass m, changing its velocity from the initial velocity to the final velocity, okay? Then after a time interval, and that object is under the influence of the force. Okay, so if you apply, there's a force applied to an object, and it changes the velocity from the initial velocity to the final velocity. Okay, so it's like the object accelerates at a given time. Okay, then remember from Newton's second law, it says that force is equal to the mass times the acceleration. Okay, from Newton's second law, okay, so from Newton's second law, it's saying that force is equal to the mass times the acceleration. You can't change that. Okay, so, and remember the acceleration is equal to what? From our kinematics, when you're calculating the motions, we are seeing that acceleration is equal to the change in velocity divided by the change in time. Okay, so if we define that, this is the final velocity minus the initial velocity divided by the initial times. Okay, that's the time changes, the difference between the initial time. So if we plug in that into this equation, what do we have? We have that the mass equals to, bringing that part into here, gives us velocity minus the initial speed divided by the changing in time. The time it changes to move from the initial position to the final position. Okay, so if we just multiply that out, then we have a mass times the final velocity divided by the time change, or you can say the final time, minus what? The initial, mass times the initial speed, this is a u, divide this by the initial time. I can put the initial time here. It's not important. Okay, let me just put change in time. Okay, then what is this? Okay, so it means what we have here is what? Okay, so I can put that as the mass times the change in velocity, because the velocity is changing, divided by the change in time. Okay, so I can bring that change to the other side. Then I say the change, because this is constant, mass is constant, of the mass times the velocity divided by the change in time. What do I have? I have that is the momentum. Remember, we defined momentum as what? As equals to the mass times the velocity. So it means this part here, it's our momentum. So therefore we have that value is equals to the change in momentum divided by what? Divided by the change in time. So it is the same as this one here. I can say this is the final momentum. It's the final momentum, okay, divided by the time taken to change that, minus the initial momentum divided by the time taken. I can combine this equation and this have it equals to the change in momentum, because the denominator is the same, divided by the change in time. Okay, so we have a very important equation here, which is the same as that one there. So, and on our left side, we have that force. Okay, so it means our force is equal to the change in momentum divided by the change in time. So what does this equation tells us? Okay, so it says that for a force applied, okay, so if you apply a force, it's equals to the object's change in momentum at that interval, change in time. So I can write that equation and say change in momentum is equals to the force times the time it takes to change the velocity. Okay, so from this equation, so it means it's saying that the change in momentum is equals to the force applied times the time it takes, okay, to change the velocities. Okay, so and what does this have? So we define force times the change in moment times the change in time being equals to the I. And what is I? Our I is the impulse, which means that, remember, the force is acting. Okay, the force is acting onto that object. So the impulse acting on that object is equals to the force applied to make that object move or to make that object change times the time it takes to change from, or to change into its momentum, or to change from the from that position, or change from the velocity, the time it takes to change from the final velocity and the initial velocity. Okay, so we define our impulse as that. So the impulse is simply equal to the change in momentum. So if we define that, so if we plug this equation into here, because that's two equations are equal, then we have that the change in momentum is equal to the impulse. So it means that the impulse is the one which is responsible for the object to change in momentum. Due to what? Due to the force applied to that object. Okay, so this is simply what we have done there. So we have that if you apply that, we have into that equation, which is the force times the change in time. Okay, so we get that. So the change in momentum is what is called an impulse, and it is what I defined earlier. So impulse is equal to the force applied times the change in time. So when you look up on this equation, so the impulse also is measured in kilogram per meter second. So the unit of the momentum and the impulse is the same. Or from here also, the unit, as I was saying, you will find that sometimes we have a unit of Newton times seconds. So it's coming from here. Remember, the force is always in newtons and the time is in seconds. Okay, so the impulse is also a vector. It also tells you the direction, and the direction of the impulse, it's the same direction as the object momentum, or I can say also the same the direction also is the same as the force applied, the direction of the force applied to that object. Okay, okay, so the impulse is the same. Okay, I will get back to you, Christine. Okay, so the impulse acts on the object while the momentum is on the object. Okay, so this one acts on the object while the other one is on the object itself. Okay, so since we know, as I was saying, we know that the impulse is the change in momentum, then from this equation, okay, from this equation that we had here, from this equation, then we equate it to that equation, as I said, then we have that the change in momentum is equal to the impulse. Okay, so then that equation is what either we have impulse equals the change in momentum, or we simply equate the force times the change in times equals the change in momentum, or we put the values when we are calculating. Then that equation, okay, this equation here is what is called the impulse momentum theory, or we can say the impulse momentum principles. Okay, so it says that the impulse of a force acting on an object is equal to the change in momentum of that object. There was a question from Christine. What were you saying?
Miss, I just wanted to know, like, I didn't understand the part that you were explaining about the impulse and momentum, like the relationship between it. I didn't really get it.
Between the impulse and the momentum.
Yes, miss.
Okay. Who's in class and you're having a song? Okay, what I was saying is, okay, so what I was saying is, who is this? Okay. Okay, if this is an object, in order for this object to change, okay, it's saying it requires a force. Okay, so now let's say this object moves or change with in speed, change its speed from the initial speed to when it is at this position, it is final speed. So it change as this object is moving, it change its speed from the initial speed to the final speed. Okay, and for this object to change, remember it says it changes within a time interval. For this object to move from this position to that position, there was a time interval. Okay, so we say that from the Newton's second law, force is equal to the mass times what? Times the acceleration. Okay, and then we define the acceleration from the questions of the motions when we're talking about when we define the accelerations is equal to the change in the velocity divided by change in time. Okay, so if we put this one into here, then we have that the mass is equals to the change in velocity divided by what? Divided by change in time. I can interchange. You remember that multiplication is commutable, so I can interchange this and say, okay, I can bring the delta here, which is change, then I can write the mass times the velocity, divide by what? Divide by the time, the change in time it takes for changing it is in velocities. Okay, then what is mv? The mv, we said that the momentum of an object is equals to the mass of that object times the velocity of the object. So it means we can write this as the change in momentum divided by change in time. What do we have? So it means this side is equals to the what is on the left hand side. So we have that force is equal to the change in momentum divided by the change in time. So I can interchange this and say, okay, my change in momentum, making the change in momentum be the subject of the formula is equals to the force applied times the change in time. So it means that the force applied, remember we said that in order for the object to change momentum, then there is a force needed. So it requires a force for the object to change in momentum. So it means the force applied is the one which is responsible for the change in momentum. So it's saying that the force applied times the change in time, it equals to that change in momentum. So what is that value? So we define that the one which is responsible for that, we give it one value, as we say it's an impulse. Okay, so the impulse is equal to the change in momentum, or we define impulse as the change in momentum. Okay, so if we are defining that the impulse is equal to the change in momentum, then that means what is equal to the change in momentum is what is equal to the impulse. Okay, so impulse is equal to the force times the time, the change in time. Okay, so if now we know that, okay, force times the change in time is equal to the impulse, then we can have a relation that connects the change in momentum to what? To the impulse, by simply substituting this one into here. So then we have that change in momentum is equals to the impulse, because we had that a change in momentum is equals to the force applied times the time. Okay, and we define that impulse, which is equal to the change in momentum, is equals to the force times the change in time. So therefore these two, remember, if you look on the left, on the right sides, this one is equals to that one. So therefore what is on the left side should be equal, and that is what yields us to that equation. So therefore change in momentum is equals to the impulse, and this is what is called um, impulse momentum theory, or we can say impulse momentum principle. It's just the theory that connects the momentum to an impulse. Or I can say the change in momentum is equals to force times the change in time. Because the change in momentum, this is how it's, the change in, the impulse, this is how it is calculated. Okay, and then the change in momentum, you are saying is mass times the velocity. Okay, so then all this one here are what we call the impulse momentum theory. Do you understand it now?
Yes, ma'am, I really understand it.
Okay, so an example here. Okay, it says a supersonic bomber with a mass of 21,000 kilograms depart from its home airbase with a velocity of 400 meter per second Joule. Okay, it's in east direction. What is the jet's momentum? Okay, so what we are given the mass and we are given the velocity. So we simply use, it's asking to calculate what the momentum is. Okay, so the momentum is equals to the mass times the velocity. Okay, so if we plug in there, we have that the mass is equal to that on the east. The velocity is that into east. So we calculate that, and remember we say that the momentum is a vector, so it should have the same direction as the direction of the velocity. Okay. So number two, it's saying, let's assume the bomber, okay, the one from example one, came to a halt on the ground. So it's like it landed on the ground. What is the impulse applied? Okay, so remember we said that just from the equation that we were doing now, we say that the impulse is equals to the change in momentum. So therefore, the velocity, you can say, okay, the final velocity when it landed at the ground is equals to 0. Okay, so it starts with initial momentums. Okay, so remember when you have change, it says the final momentum minus the initial momentum. So we have calculated what our momentum it is as it just started. Then we have that the final momentum is equals to 0. Okay, minus the momentum that we calculated at the initial, which was I think it's 84,000 whatsoever is that one, the numbers there, you can check on the example. And this one was on east. Okay, so if we calculate this one, we are saying it's a minus 84 whatsoever that value that we had there on east. But what does this tell us? If you go to a Cartesian plane and you are saying, okay, this is east and this is west, this is south. Okay, so it's saying that it's going with a negative of momentum of that. Okay, over that on that direction. Okay, so it say it's, if you look up on this one and you look on the first value, it simply means it's a reverse of the initial direction. Because of this minus, it's already telling us in which direction is it going. Okay, so it means our answer is simply equals to that value to what? To west. Because we already have a negative sign, so it means it's simply going with that value in which direction? Into the west direction. It means it changes the directions from east to west. Then the second third equation that we have here, or third example, is saying if a football if the football halfback experience a force, okay, moving back with that force of 800 Newton for 0.9 seconds, okay, to the north, determine the impulse. We even forgot to put our direction here. So remember, we are saying that the impulse is equal to the force times the change in time. Okay, we are given the force and we are given the time it takes. So simply plug in there, and we are saying the impulse is also a vector. So the direction of that one is also to the north, because this one it's saying also, it's saying that the force is due to the north. So therefore, our impulse is also on the direction of the force experience. Okay, so if we look into the fourth example, it says that a tow truck applies a force of 2,000 newtons on a 2,000 kilogram car for a period of 3 seconds. What is the magnitude of the change in the car's momentum? Okay, so we simply calculate the magnitude here. So where it's saying that, remember from our equation, where we had equation 4 that says that the change in momentum is equal to the force times the change in time. So if you put in these values, because we are only required to calculate the momentum, because they are only given the magnitude of the force and not all the direction. So therefore, this is equals to the force, magnitude of the force times the time it takes, okay, which is equal to the 6,000 Newton a second, or 6,000 kilogram per meter second. I emphasize wants to go into the fourth one here. A tow truck applies a force, it's the same one there. Then this one is asking if the car starts at the rest. If that car starts at the rest, what will be its speed after 3 seconds? Okay, it starts at rest, which means that it starts with the velocity equals to 0. Okay, so the initial velocity is equals to 0. Okay, and you are asked to calculate what it is final velocity. Okay, from the impulse momentum theorem, it says that the change in momentum is equals to the impulse. Okay, so where the impulse is the same as the force times the time taken. And this one we have already calculated from the first equation. So this one means that the final velocity, the final momentum minus the initial momentum is equals to that impulse. Okay, we have calculated the impulse from the previous example. Okay, and our initial velocity is equals to 0. Okay, so it means this part here is equals to 0. So we're only left with that the mass times the final velocity is equal to the impulse. Okay, so it means that a final velocity is equal to the impulse divided by what? Divided by the mass. Okay, so we have calculated what our impulse is from the thing, which was 6,000, and we given the mass of 2,000. Okay, plugging in all what we have, 6,000, and then you simply divide this with 2,000, and then we get that hour is 3 meters per second. So it means that it used the final velocity of that truck was equals to 3 meter per second. Okay, so here while waiting for a car on a stop, that one we've done the collections, so you can just go through. Okay, so it is equal to the change in momentum. We have done all those examples, but here on that equation we are being asked to find the force. Okay, so we need to start over with the conservations of the momentum, and I think that will be tomorrow or Friday. Or do you want us to continue?